Welcome everyone to The Spoken Nerd. I'm your host Connor McDonald, and as always, we're here talking database technology, just things that get my interest and hopefully get yours as well. If you're a regular follower of the podcast, you will have noticed that we've been doing a back to basics style of information sessions over the past few months. The last session perhaps took that maybe a little bit to the extreme by talking about block internals, especially without the aid of visuals. And since we've already covered how a table scan works, the next logical element to discuss in terms of back to basics would be how indexes work. However, I'm going to defer that until the next episode because I feel most people are aware of what an index does. Not necessarily how it works, but certainly what it does. And that is, if it takes a while or it's too slow to get some rows out of a table, the general consensus is that you add an index and somehow magically that will make things faster. So don't get me wrong, we will indeed talk about how indexes work, but today's topic is a more important one in my opinion, and that is what you perhaps have already gleaned from the somewhat controversial title, namely, every index that you have in your database is due to a bug. Or you could even shorten that to every index is a bug. Now hold on there. Don't sign off the podcast just yet. Hear me out. Let me justify that statement. Let's dial things back right to their most basic and raw form. If you are querying data, if you need to find a single row in a table that only consists of a single row, do you need an index? No. Don't get me wrong. I have an existing video on my YouTube channel that shows that having an index on such a table may be of benefit. But in terms of how long will it take to find a single row in a single row table, the answer is no. You don't need an index for the vast majority of the time. What if I wanted to find a row in a 1,000 row table? There's a good chance you probably don't need an index to speed up that as well. 1,000 rows probably fits in just a smattering of blocks, and with modern hardware you could read that incredibly quickly. What about a row in a 10,000 row table? Well, now we're starting to get into the realm of maybe I might need an index. Probably if I get to the point of finding one row in a 1 million row table, then there's a probably good chance that an index is going to assist here. But notice none of this discussion is about your data. It is purely about fixing an underlying limitation in the implementation of the technology. If hardware was infinitely fast, I would never need an index for a query. If I could locate a single row or a very small subset of rows incredibly quickly, no matter how large the data set was, why would I ever add an index just to improve the query performance if the query performance was already sufficient? So my point here is for the querying of data, the retrieval of data from the database, an index is only ever present to fix an underlying limitation, or let's call it a bug, in the hardware stack. Your hardware is too slow, and therefore an index is some mechanisms of working around that bug. Of course, indexes are not solely about retrieving data. Indexes are also a necessary part of controlling data quality. And let's face it, that is predominantly why we store data. We store data to have some associated value of that data at a later time. It may be working out customer sales trends. It may be measuring critical data to ensure that your machinery doesn't fail. There is always an associated value with data, and that's why we store it. Also associated with your data is a level of trust that you're prepared to forsake in that data. What do I mean by trust, or the trust level of your data? Let me give you a couple of examples. If I had billions of rows in a table, and each of those rows consisted of some measurement I've made about the flight patterns of birds migrating south for the winter, 10% perhaps of that data could be incorrect or wrong. I probably don't care. A 90% correct sample of 1 billion rows of bird flight patterns is more than sufficient to give me excellent predictive and analytical views of the flight patterns of birds. Conversely, if I had the same number of rows, 1 billion rows of financial transactions of customers, if only 0.0001% of that data is incorrect, then rest assured, I care a lot Or someone else, probably your customers, cares a great deal about that level of inaccuracy. Thus, the critical things for data are the associated value of the data and the level of trust that we require of the accuracy of that data or its quality. Indexing is not just about querying of data. Indexing is part of the implementation of how we guarantee the quality of our data. Let me go through those same scenarios I spoke about with querying data when it comes to enforcing data quality. If I have a single row of data in a table and no mechanism to add more data, it is a single row always. Do I need an index to ensure the quality of that data? I probably don't, because the concept of duplication doesn't exist in a single row table on the assumption that another row can never be added. What if my table has 10 rows and I want to ensure the data quality by having no duplicates in there? Don't get me wrong, I know that in the real world implementation of databases, we would require an index to do this. But in a theoretical premise, we could probably get away with no indexing to ensure that data quality. The implementation would be whenever someone tries to modify one of those 10 rows, we would simply check all the other rows, and then if there are no duplicates, we would commit the change. The time it takes to check those 10 rows would be so incredibly fast that we could ensure the consistency of the data in that time frame. When I scale this out to a larger number of rows, that model breaks down. If I have 10,000 rows in my table, I probably will need an index to ensure that duplicates cannot occur. If I didn't, what would happen is I could insert a row, but during the time it takes to check all the other rows to make sure there are no duplicates, someone could, for lack of a better term, sneak in behind me, head to a part of the table that I've already checked, and insert a row which would then form a duplicate. To avoid that, I could lock the entire table while I make modifications to the data, and then while I hold that lock, ensure there are no duplicates before I do a commit. Once again, we are heading into the territory of a bug or limitation of the underlying hardware. In my 10,000 row table, if I could lock the table, allow rows to be modified, then check all 10,000 rows to make sure there are no duplicates, and then commit the change in an infinitely small amount of time, then why would I bother with an index? The index is solely there to ensure that I can do that kind of processing to guarantee no duplicates, no data corruption in an acceptable response time for my applications. By this point, you're probably going, thanks, Connor, you're presenting to me a case for no indexes in a magical land where fairies and pixies might exist and hardware is infinitely fast. Don't get me wrong, I understand we are not in a utopian state, thus indexes are a necessary evil. But that is my focus here, that is my point. If you want to have really successful database applications, I like to adopt a mindset of treating an index as a necessary evil as opposed to some element of databases that are automatically required, that are always there. If you can get your mindset around the fact that an index is something you would rather not have at all, but implement them just when required, I think you actually have far more successful applications. For me, an index is exactly the same as any other component, hardware or software, that you may choose to adopt for your database. That is, it is always about cost versus benefit without exception. For example, if I'm going to buy some more memory for my laptop, the memory might cost $200. I need to make a cost-benefit analysis of will that $200 yield me a dramatic performance improvement on my laptop? The fact that I'm running Chrome on my laptop probably means there is no amount of RAM that's ever going to make it run well. Maybe it's time to move to a new browser. So let me go through some of the common indexing requirements we have in our databases, but address them strictly from a cost versus benefit ratio. Because if we can do that, then we're going to come up with the perfect amount of indexes for our applications, and we're always going to be cognizant of the fact that the indexes we have are giving us the best bang for their buck, so to speak. We're not having any redundant indexes on our applications. First off the bat is the most obvious one, primary keys and unique keys. Yes, you must have an index to support those constraints in your database. As I mentioned before, it's just not practical to lock a table for an extended period of time to make sure that uniqueness or primary key violations never occur. Thus, the cost element is pretty much fixed, i.e., I must have the index, it's mandatory. But in terms of improving that cost-benefit ratio, maybe then I can bump up the benefit side of the equation. By default, your primary or unique key constraint will have a unique index supporting that definition. However, you might be able to get some more benefits out of that index by making it a non-unique index. Why would I do that? I may be having a requirement for occasional data maintenance to ensure the data quality is at the levels I require. As a result, I might want to make that constraint deferrable from time to time, and having a non-unique index also permits that. But don't forget, it's a cost versus benefit calculation. A non-unique index that supports a primary key constraint typically will use a little bit more space, and also you'll generally do a bit more latching when you actually are doing primary key checks as data is being inserted, because I can no longer just do a one and done kind of lookup. The database itself, if it knows the index is non-unique, must do a probe into the index and then just make sure there isn't another entry as well of the same key value. For primary and unique key constraints, the index is mandatory, but we can still focus on the benefit side of the equation to see if we can get the best return on our index investment, for lack of a better term. Let me move on to foreign key indexes now. This is perhaps a controversial one because one of the most common performance issues we see in databases is a lack of indexes on foreign key columns. However, I want to flip that conversation around. There is a myth associated with foreign keys, and that is that every foreign key should be indexed. And you'll see this on blogs, videos, etc. People saying every foreign key should be indexed to avoid locking issues. And that advice is just plain wrong. Now, I don't want to be critical of people who say you should always be indexing their foreign keys. However, a lot of that advice is based on the history of the Oracle database. Back in the day, when we first introduced referential integrity constraints in Oracle 7, if you had a foreign key between a parent and a child table, pretty much if you touched the parent in any way, shape, or form, you made any modification to the rows, we pretty much locked the child table for as long as the transaction was open. It was our first implementation of foreign key relationships. The only way you could avoid locking the entire child table when you made a modification to the parent table was to add a foreign key index. In particular, this was the era of client-server applications. So having a child table locked in its entirety for the duration of a transaction was a big deal because applications were stateful. You could start a transaction, walk away from your machine, go to lunch, and that child table is locked for the duration of your lunch break. A great way to make you very, very unpopular with the rest of your IT friends and users. In these early days of the Oracle database with referential integrity constraints, adding an index on the foreign key columns in the child table was a no-brainer. But I stress, this is solely about cost versus benefit. The cost of not having the index was huge, massive locking issues, and therefore the cost-benefit analysis was a no-brainer. But a lot of people have never revisited that advice because the technology has changed over the years. I think it was around about Oracle version 9. We changed the implementation such that it wasn't for the duration of the transaction that we would hold a lock on the child table if there wasn't a foreign key index. It was about the length of the statement. You performed an operation on the parent table, some sort of DML, and only while that statement was running would the lock be held. The moment it finished, the lock would be released, and it didn't matter how long you waited in your application until the actual commit was performed, thus ending the transaction. There was still a potential for locking the entire child table, but that lock was a much shorter duration now. Unfortunately, I remember back in the day, a lot of the information that was published about this was that we had solved the locking issue. Probably a poor choice of words. We had simply shortened the duration of the lock. Still, a very worthwhile improvement, but very few people took this on board. The advice of the time was still, yes, you definitely need to have a foreign key index on all foreign keys. The changes in Oracle 9i, I think, had already started to make that advice somewhat dubious. But if we fast forward to modern versions of the database, we have continued to evolve our processing when it comes to DML operations on the parent. Nowadays, the only things you really need to be concerned about is, are you messing about with the primary key columns on the parent? And when I say messing about, it simply means, are you deleting a row from the parent, or are you updating the primary key columns? We don't need to worry about insert on a parent table, because if you are inserting on a parent table, then by definition, there is not yet a row in the child table because we have a foreign key relationship. So we're only going to lock that child table for the length of the statement execution, and only when you're deleting the parent or modifying the parent primary key. Think about your own applications and how often do you actually do that? Don't get me wrong, it's not never. Let me give you some examples. If I have a typical sort of order entry system, if I'm deleting an order from my system, someone has cancelled an order, and that order might contain some child information, a list of items in that order, then it's probably a plausible scenario. Someone wants to cancel an order, we may delete it such that it never existed on our system, which means we need to delete the parent and delete the child rows as well, which means we need to delete the parent order and delete the child items for that order as well. That's a plausible application requirement, in which case you would definitely need a foreign key index on the child order items table, because you are probably going to be deleting orders, the parent table, from time to time. However, in the same application, sitting above our orders table is probably a customers table. Customers have orders. Are you ever going to delete a customer? It's never going to happen. There is no way a customer delete function in your application is going to be, yes, I'm going to delete the customer row and I'm going to delete all the orders for that customer as well. We just don't do those kind of things in financial applications. We would mark a customer row as deleted in order to retain the order history. So in that case, the requirement of a foreign key index to avoid locking issues for deletion of a customer is pretty much not going to be there, because you're never going to delete those customer rows. Therefore, you're never going to end up with a lock on the orders table, which is the child of customer. But there is a second question to be asked here. Is it likely that a customer will log on to your application and say, show me all of my orders? Show me the orders for a nominated customer. Most probably yes. And in that case, we probably will need an index on the customer column in the orders table. This, however, is not to satisfy a foreign key locking issue. This is simply to satisfy a query performance issue. I keep stressing, indexes are a cost versus benefit decision. I would rather not have an index on customer, but if I'm going to often be requiring queries to search by customer, the index becomes a significant benefit. But let me throw one more example at you. In this similar order entry customer kind of system, I probably have a list of products, because as customers make orders, they will choose from a list of products. Am I likely to delete a product from my system, as in a physical delete operation on the product table? I would argue that would never ever happen. Once again, you're not going to descend into my orders table of existing customer orders and delete all the orders just because I want to remove a product from my catalog. I'm going to mark that product as no longer available, or no longer an option for a customer to choose. Therefore, it is unlikely I will need a foreign key index on the product column in my orders table, because I'm never going to delete the parent. In the same way as I spoke about the customer index, the second question I need to ask is, am I likely to look at all the orders for a particular product? And we come back again to cost versus benefit. If I am going to look at orders for a particular product, if it's for a particular customer as well, the customer index is probably fine for that. If it's for a product across all orders, well, how often am I going to be doing that? Is that going to be a trend analysis style of query? Am I going to be looking at all orders for all time? If that's the case, maybe a full table scan is going to be better anyway. Maybe I'm hash partitioning my orders table for performance concurrency, and therefore I can cope with using a parallel query across all the partitions to find information for a particular product. Maybe I'm coming in for a particular order number anyway, or a particular date range of orders. Depending on my application requirements, I may or may not need an index on the product column in my orders table, but one thing I do know is I definitely won't need it simply to solve foreign key locking issues because I'm never going to delete from my product table. Hopefully you can see where I'm going here. Every index is cost versus benefit, not some sort of automatic rule that tells me, oh, it's a foreign key, I must have an index. Let me move on to what I call the percentage myth. Plenty of blogs out there will have some arbitrarily picked percentage number that is critical for an index. They'll say, if your query needs to return 1% of the rows in a table, you need an index. Or if you need to return 5% of the rows in a table, you need an index. That is complete tosh. The rule is once again simple. Cost versus benefit. You might need to get 1% of the rows back. You might need to get 50% of the rows back. You might need to get 80% of the rows back. It is nothing to do with the percentage. It is purely cost versus benefit. When we're deciding cost versus benefit, we say, I have a set of rows I need to get back to the application or the user or the customer in an acceptable time frame. Does my application do that without having the index there? If it does, I'm done. Why would I add an index for no benefit? Conversely, if adding an index still does not get the results back to my application or customer in an acceptable time frame, then no, I would not put the index on. I get no benefit and I get a lot of cost. If the index does improve the performance to the level that it does get the data back in an acceptable time frame to the application or customer, even then I'm not done. I've solved the benefit side of the equation. I get the results back fast, but what does it cost me? And does that cost outweigh the benefit? That cost could be slower DML performance. It could be increased redo, a slower backup time. A lot of those things we often don't really worry about too much because it's just a single index. But one of the other things we also need to be very cognizant of is what impact does that index have on the existing code in my application? Execution plans can dramatically change with the addition of a new index. One of the beauties of our automatic indexing in 19C is that we very carefully look at regression testing as well. Adding an index can be an enormous risk to your application because any query that involves a table for which that index has just been added could potentially change. That's a big set of regression testing and therefore a big cost that you need to weigh up in terms of the cost-benefit ratio. Along similar lines in terms of people picking arbitrary percentage values is what I call the bitmap index myth, where rather than percentages, people will choose the number of distinct values. If there are 2 distinct values, then you need a bitmap index. If there are 10 distinct values or 1,000 distinct values, etc., then you should use a bitmap index instead of a normal index. Once again, this is a myth. There is no discernible difference between a bitmap and a B-tree index when you have that mindset of does the benefit outweigh the cost? I've seen many applications where columns have a very low number of distinct values, yet they want to perform queries on those columns and therefore bitmap indexes have been added. But that really isn't where bitmap indexes come into their own. If I have a database table with details about people, a bitmap index on gender is going to be useless if I search for all the people that are female or male, because there are large volumes of the data with either value. If there's a bitmap index on the hair color, once again, each different value for color of hair probably has many, many rows. An index, bitmap or otherwise, is unlikely to be good for such queries. Where bitmap indexes really come into their own is when you're combining multiple columns, each with a low number of distinct values. If the kinds of queries I ask of my people table is show me all the females in a particular suburb above the age of 40 who have red hair, then that's where bitmap indexes on each of those columns can be very, very efficient. If I'm just searching on one of those columns, bitmap indexes are not going to be useful, and therefore the cost outweighs the benefit. It's always cost-benefit analysis. And finally, and perhaps most recently, is what I call the Exadata myth, where proponents will say, because I have an Exadata with its amazing storage subsystem, I don't need any indexes at all. But Exadata, like foreign keys, like bitmaps, like everything else, the rule is exactly the same. Cost versus benefit. The only difference with Exadata is that the cost-benefit calculation has changed. Table scans are that much better on an Exadata system that the index has to work harder, so to speak, to justify itself. Whereas an index might be appropriate in a non-Exadata system, it might well be the case that it is no longer required in an Exadata system because the benefit of a table scan is that much better. But it is still cost versus benefit. As I wrap up this podcast session, you might be coming away with the impression that I am somewhat anti-index. There's sort of a religious fervor here. That is not the case. My point of view is with any piece of technology of which indexes are just an example, it is always the duty of the practitioner to explore the cost versus the benefit. And even when you come to the point where an index is required, you can still focus on the elements of minimizing the cost of that index and maximizing the benefit. Let me give you some examples of that. Indexes have a basic compression facility where the storage of the index uses mechanisms to eliminate duplicate values, therefore making the index more dense, more tightly packed, and hopefully more efficient, an improved benefit for the existing cost. We have partial indexing strategies for partition tables, but also even without partitioning, you can use function-based indexes to index just part of a table. This is another example where you could make an index smaller and more targeted at just retrieving a certain subset of data from your table, once again reducing the cost while keeping the same benefit. And finally, perhaps the one I don't see that often and I think really is a missed opportunity for so many applications are domain indexes, or the most common example being text indexes. Many applications that we build end up with 3, 4, 5, 6, 7 indexes on a single table in order to serve ad hoc search requirements. But the typical consumer nowadays of your applications associates search with browser level search, i.e. I just want to type in some keywords and I need you to find the rows. We see that functionality by default in all of our Application Express tools. The ability simply to type in a search expression at the top of an interactive report, for example. A domain index is a great way of capturing the values in multiple columns and putting them into a text index and just doing keyword searches. In that way, you can offer a browser search style of indexing to your applications and hopefully get away with removing many redundant indexes on individual columns. I know I sound like a broken record, but that improves the benefit and reduces the cost because now you just have a single index. Let's wrap it up there. Hopefully you get the idea of my mindset of using indexes in your databases. It's not necessarily about minimal indexes. It's about always making that decision of, do I really get the benefit from an index given that it always has an inherent cost? If you can keep that mindset front and center, then you'll end up with just the right amount of indexes. Let's call it the Goldilocks indexing principle. You don't have too few indexes, but you don't have too many. You have just the right amount. Thanks very much for listening, everyone. Hopefully you enjoyed this one. In our next podcast episode, we'll jump into how indexes are actually stored. I'll see you then. Thanks for listening to this podcast. The music credit goes to Zanman from Pixabay Music.